Basic impulse insulation level, or BIL, is indeed the insulation strength expressed in terms of the crest value of the withstand voltage of a standard lightning impulse voltage wave. To gain a better understanding of this subject, you can consult several resources. Firstly, consider IEEE Standard C62.21-2019, which is the IEEE standard for surge protectors for AC power circuits. This standard provides detailed information on BIL and surge protection specifically for AC power circuits. Secondly, IEEE Standard C37.10-2019, the IEEE standard for application of surge arresters for alternating current systems, offers guidance on the application of surge arresters in AC systems, and importantly, it includes information on selecting the appropriate BIL. Thirdly, the book Electrical Power Systems Quality 3rd edition, authored by Roger C. Dugan, Mark F. McGranagan, and Sari Santoso, features a chapter dedicated to insulation coordination and surge protection, covering BIL in significant detail. Furthermore, you can find information on BIL in the IEEE color books, specifically the IEEE Buff book, which is focused on electrical power equipment maintenance and testing. This book has a chapter dedicated to BIL testing. Also, the IEEE Green Book, titled Handbook for Electrical Power Distribution Engineering, contains a chapter on insulation coordination, which also addresses BIL. These resources should give you a more complete understanding of what BIL is and how it is applied in power systems. BIL is a crucial parameter in the design and operation of electrical equipment, especially in switchgear and other high-voltage apparatus. It represents the capability of the insulation system to withstand transient overvoltages caused by lightning strikes or switching surges. A higher BIL indicates a greater ability to withstand these surges without insulation failure. The standard lightning impulse voltage wave used to determine the BIL is a specific waveform defined by industry standards. It has a rise time of 1.2 microseconds and a time-to-half value of 50 microseconds, often referred to as a 1.2 by 50 microsecond wave. The crest value of this wave, the maximum voltage reached, is the voltage level that the equipment's insulation must be able to withstand during testing to meet its specified BIL. Understanding BIL is important for several reasons. Firstly, it helps ensure the reliability and longevity of electrical equipment. By selecting equipment with an appropriate BIL, engineers can minimize the risk of insulation failures due to overvoltages, which can lead to costly repairs and downtime. Secondly, BIL plays a key role in insulation coordination. Insulation coordination is the process of selecting the insulation strength of various components in a power system to ensure that insulation failures, if they occur, happen in a controlled and predictable manner. This helps to protect more critical equipment from damage. Thirdly, BIL is directly related to surge protection. Surge arresters are devices designed to protect electrical equipment from overvoltages by diverting surge currents to ground. The selection and application of surge arresters must be coordinated with the BIL of the equipment being protected. The surge arrestor should have a protective level that is below the BIL of the equipment, ensuring that the arrestor will operate before the equipment's insulation is stressed beyond its withstand capability. When evaluating switchgear specifications, the specified BIL indicates the level of overvoltage protection the equipment is designed to withstand. A higher BIL rating generally means the equipment is more robust and can withstand larger surges. However, higher BIL equipment may also be more expensive. Therefore, selecting the appropriate BIL involves balancing the need for protection with cost considerations. In practice, the selection of BIL involves several factors, including the system voltage, the expected frequency and magnitude of overvoltages, the altitude, and the environmental conditions. Higher altitudes and certain environmental conditions can reduce the insulation strength of equipment requiring a higher BIL. The IEEE standards mentioned previously provide detailed guidance on how to determine the appropriate BIL for different applications and conditions. These standards also provide information on testing procedures used to verify that the equipment meets its specified BIL. These tests typically involve applying the standard lightning impulse voltage wave to the equipment and verifying that the insulation does not fail. The above book provides additional details on these testing procedures. In addition to the IEEE standards and color books, you can find information on BIL in textbooks and other technical publications on power systems engineering. These resources often provide a more general overview of the topic, which can be helpful for developing a foundational understanding. It is also worth noting that BIL is closely related to another important insulation parameter called the switching impulse insulation level, or SIL. SIL is similar to BIL, but it uses a different impulse voltage wave that is representative of switching surges rather than lightning surges. Switching surges are caused by events such as opening and closing circuit breakers or energizing transformers. The SIL is typically lower than the BIL, but it is still an important consideration in insulation coordination. In summary, BIL is a critical parameter in the design and operation of electrical equipment. Understanding what it represents and how it is determined is important for ensuring the reliability and safety of power systems. By consulting the resources mentioned, including the IEEE standards, color books, and textbooks, you can develop a comprehensive understanding of BIL and its applications. Now let us go into a deeper dive regarding what a lightning impulse voltage wave is and how it is related to BIL. The standard lightning impulse voltage wave is a precisely defined waveform used to simulate the effects of lightning strikes on electrical equipment. This waveform is characterized by its rapid rise to a peak voltage followed by a slower decay. The shape and duration of this wave are standardized to ensure consistent and repeatable testing of equipment insulation. As previously mentioned, the standard lightning impulse voltage wave has a rise time of 1.2 microseconds and a time to half value of 50 microseconds. The rise time refers to the time it takes for the voltage to increase from 10% to 90% of its peak value. The time to half value is the time it takes for the voltage to decay from its peak value to 50% of its peak value. These parameters are critical because they influence the stress that the voltage wave places on the insulation of the equipment being tested. The rapid rise time can cause high voltage gradients within the insulation, while the longer decay time can lead to thermal stress. The crest value of the lightning impulse voltage wave, which is the maximum voltage reached during the test, is the key parameter used to define the BIL. The equipment's insulation must be able to withstand this voltage without flashover or breakdown. Flashover refers to a disruptive discharge over the surface of the insulation, while breakdown refers to a disruptive discharge through the insulation. Both flashover and breakdown can damage the equipment and lead to system outages. The standard lightning impulse voltage wave is generated using specialized equipment called an impulse generator. An impulse generator typically consists of a series of capacitors that are charged in parallel and then discharged in series through a shaping network. The shaping network is designed to produce the desired waveform with the correct rise time and time to half value. The output of the impulse generator is then applied to the equipment under test, and the voltage and current are monitored to detect any signs of insulation failure. The testing procedure for determining the BIL of equipment is described in detail in the relevant IEEE standards. These standards specify the number of impulse voltage waves that must be applied, the time interval between impulses, and the criteria for determining whether the equipment has passed the test. Typically, the equipment must withstand a certain number of impulse voltage waves without any flashover or breakdown. The BIL of electrical equipment is typically specified by the manufacturer and is based on the equipment's intended application and operating environment. For example, switchgear used in outdoor substations will typically have a higher BIL than switchgear used in indoor applications. This is because outdoor equipment is more likely to be exposed to lightning strikes. The BIL is also influenced by the system voltage. Higher voltage systems generally require equipment with higher BIL ratings. This is because higher voltage systems are more likely to experience overvoltages due to lightning strikes or switching surges. In addition to the system voltage and operating environment, the BIL is also influenced by the altitude. Higher altitudes have lower air density, which reduces the dielectric strength of air. This means that the equipment at higher altitudes is more likely to experience flashover. Therefore, equipment used at higher altitudes typically requires a higher BIL. The IEEE standards provide guidance on how to adjust the BIL for altitude. In summary, the lightning impulse voltage wave is a standardized waveform used to simulate the effects of lightning strikes on electrical equipment. The crest value of this wave is used to define the BIL, which is a critical parameter in the design and operation of electrical equipment. The BIL is influenced by several factors, including the system voltage, the operating environment, and the altitude. The IEEE standards provide detailed guidance on how to determine the appropriate BIL for different applications and conditions. Now let us discuss the relationship between BIL and surge arresters. Surge arresters are essential components in electrical power systems that protect equipment from damage in overvoltages. They work by providing a low-impedance path to ground for surge currents, diverting the surge away from the protected equipment. The surge arrestor is designed to operate when a voltage exceeds a certain threshold, called the protective level. The protective level of the surge arrestor must be coordinated with the BIL of the equipment being protected. The protective level must be below the BIL, ensuring that the arrestor will operate before the equipment's insulation is stressed beyond its withstand capability. If the protective level is too high, the equipment may be damaged by the surge before the arrestor operates. If the protective level is too low, the arrestor may operate unnecessarily, leading to nuisance tripping. The selection of the appropriate surge arrestor for a particular application involves considering several factors, including the system voltage, the expected surge current, the protective level, and the energy handling capability. The surge arrestor must be able to withstand the expected surge current without failure. It must also have sufficient energy handling capability to dissipate the energy associated with the surge. The IEEE standards provide detailed guidance on the selection and application of surge arresters. These standards specify the performance requirements for surge arresters and provide methods for calculating the expected surge current and energy. The standards also provide guidance on coordinating the protective level of the surge arrestor with the BIL of the equipment being protected. The location of the surge arrestor is also important. The arrestor should be located as close as possible to the equipment being protected. This minimizes the impedance between the arrestor and the equipment, reducing the voltage drop across the impedance during a surge. The arrestor should also be properly grounded to ensure that the surge current is effectively diverted to ground. In summary, surge arresters are essential components in electrical power systems that protect equipment from damaging overvoltages. The selection and application of surge arresters must be coordinated with the BIL of the equipment being protected. The protective level of the surge arrestor must be below the BIL, ensuring that the arrestor will operate before the equipment's insulation is stressed beyond its withstand capability. The IEEE standards provide detailed guidance on the selection, application, and coordination of surge arresters. Now we will talk about insulation coordination, which is the process of selecting the insulation strength of various components in a power system to ensure that insulation failures, if they occur, happen in a controlled and predictable manner. The goal of insulation coordination is to protect critical equipment from damage and to minimize the impact of insulation failures on system reliability. Insulation coordination involves considering several factors, including the system voltage, the expected overvoltages, the BIL and SAL of the equipment, and the characteristics of surge arresters. The process typically involves performing a detailed analysis of the system to identify potential overvoltage sources and to determine the magnitude and frequency of the expected overvoltages. Based on this analysis, the insulation strength of the various components is selected to ensure that the equipment can withstand the expected overvoltages with an acceptable margin of safety. Surge arresters are used to limit the magnitude of overvoltages and to protect equipment from damage. The protective level of the surge arresters must be coordinated with the insulation strength of the equipment. The IEEE standards provide detailed guidance on insulation coordination. These standards specify the methods for calculating overvoltages, selecting insulation strength, and coordinating surge arrestor protection. The standards also provide guidance on testing procedures for verifying the insulation strength of equipment. In addition to the IEEE standards, there are several other resources available on insulation coordination. These resources include textbooks, technical papers, and training courses. Insulation coordination is a complex process that requires a thorough understanding of power system principles, overvoltage phenomena, and insulation characteristics. It is an essential aspect of power system design and operation. By carefully coordinating the insulation strength of the various components in a power system, it is possible to minimize the risk of insulation failures and to protect critical equipment from damage. Now let's delve into the BOF book and the Green Book and how they can help with understanding basic impulse level, or BIL. The IEEE BOF book, formerly known as the IEEE Recommended Practice for Electrical Power Equipment Maintenance and Testing, provides comprehensive guidance on the maintenance and testing of electrical power equipment. While it may not dedicate an entire chapter specifically to BIL, it often includes discussions and procedures related to insulation testing and assessment, which are closely tied to understanding and verifying BIL. Within the BOF book, you can expect to find information on insulation resistance testing, dielectric strength testing, and other diagnostic methods used to evaluate the condition of insulation in electrical equipment. These tests help determine if the insulation is capable of withstanding the voltage stresses associated with the equipment's BIL rating. The book also covers topics such as transformer testing, circuit breaker testing, and switchgear testing, all of which involve considerations related to insulation integrity and BIL. The BOF book can be valuable for understanding how to assess the condition of insulation and verify that it meets the required BIL standards. On the other hand, the IEEE Green Book, officially titled IEEE Recommended Practice for Powering and Grounding Electronic Equipment, primarily focuses on power quality, grounding, and wiring practices for sensitive electronic equipment. However, it also contains information relevant to insulation coordination and surge protection, which are related to BIL. The Green Book provides guidance on how to protect electronic equipment from voltage surges and transients, which can be caused by lightning strikes or switching operations. It discusses the use of surge protective devices, or SPDs, and the importance of proper grounding to minimize the impact of these surges. The book also touches upon the concept of insulation coordination, which involves selecting the appropriate insulation levels for different components in a power system to ensure that surge voltages are safely managed. The Green Book may not provide an in-depth discussion of BIL, but it can offer valuable insights into how to protect sensitive electronic equipment from voltage surges and transients, which is an important consideration in the context of BIL. While the BOF book provides details on testing, the Green Book explains how to protect sensitive equipment from voltage surges and transients.